Hi everyone, welcome back to another Algebra 1 tutorial. In this video, we'll be going over solving special systems and linear inequalities. So the key concepts for this chapter is going to be consistent and inconsistent systems, solving linear inequalities, and solving systems of linear inequalities. Special systems. So there are two other pairs of systems, namely consistent and inconsistent systems, which are examples of special systems. So consistent systems are systems that have at least one solution, whereas inconsistent systems are systems that have no solution. So a consistent system can be solved using any of the traditional inequality solving methods, whereas inconsistent systems usually are something like this. So here, these two do not have any solutions, thus they're inconsistent systems. So suppose we tried solving for either one, so we have y is equal to x minus 1 as well as negative x plus y is equal to 2. We might cancel out these and then we're left with this. So maybe if we took out the x to the other side, we would get y is equal to x minus 1 and y is equal to x plus 2. So suppose we add a negative to both sides, it would still not work, since there's a singular y and there's a singular x. Thus there are no solutions for these inequalities because we can't find neither the x nor the y values. Thus it is inconsistent. We can either have both of them or we cannot have either one of them. So solving for inconsistent systems. So usually you're supposed to prove that it is false by two methods. You have to prove that it's parallel by changing it to slope-intercept form, or you have to graph the two functions and show that there is no point of intersection. So let's look at the previous problem. So we can change it to slope-intercept form, after which we see that they're the same slope. So we have y is equal to x minus 1. And if we solve the other one, which was negative x plus y is equal to 2, we get y is equal to x plus 2. And if you realize, you see that both of these lines have the same slope and different y-intercepts, which basically means that they're parallel. Another way you can solve for one, instead of proving that they're parallel, is by graphing it. So we have y is equal to x minus 1 and we have y is equal to x plus 2. So we could graph this one. So we have x minus 1. So let's graph this one over here. So y is equal to x minus 1. So we can get different coordinates. So let's use the y-intercept and x-intercept. So the y-intercept is negative 1 and the x-intercept is 1. So now we can graph the line. So we have one point over here and one point over here and there. So now we have one line. Now we can graph another one. So 2 and negative 2 would be our line. Since substitute x with 0, we get 2. So 1, 2 and negative 2. So over here. Alright, so or we can prove it by this. See, we just need to move it just like this, and we can see that without even having to move the ruler, we have the same exact ruler slope. And as you can see here, these lines look very parallel. So thus we can show that it's by graphing, as well as we can show by proving that both lines are parallel. Next, we're going to learn how to show systems of infinite solutions. So for such problems, we have to prove that both of the lines are coinciding, or they're basically the same line. So we can do that by proving that the functions are the exact same through solving, or we can prove that their graph is same by drawing the same line. For example, let's solve this one. Y is equal to negative x plus 3, and x plus y minus 3 is equal to 0. So these equations are the exact same. The only difference is the way they are solved. So suppose we simplify this one as well into slope-intercept form. We have y is equal to negative x plus 3, which is the same exact function. And if we looked at the graph without even solving for them, we would still get the same line, which looks something like this. So it usually it might look a little steep. So yeah, we would have the same exact line. So the best way to do it in this case is simplify the unsimplified function and prove that both of these lines are coinciding. So now let's do a few problems. So we want to prove that they have no solution. So we're going to be using both methods for both infinitely and no solution. So we have y is equal to x plus 1 and y is negative x plus y is equal to 3. So if we simplify this one, we get y is equal to 3 plus x, or x plus 3. And since both of these have the same slope, we can say that they're parallel. We can also do it in a different way. So we have y is equal to x plus 1 and negative x plus y is equal to 3. So we can graph them by getting the y-intercept and x-intercept. So the x-intercept for the first one would be negative 1, 0, and the y-intercept would be 0, 1. And for this one, it would be negative 3, 0, and 0, 3. So now that we have our two graphs, we can make a line. So now we have a line, negative 3, 0, and 0, 3. So 1, 2, 3, 0, 0, 1, 2, 3. So now we can connect the dots for this one first. And then we can do it for this one as well. So negative 3, 0, negative 1, 0, and 0, 1. And as you can see here, it immediately looks parallel because you can see no lines of intersection. So this is another way to prove that there's no solutions, by showing that these two lines have no points of intersection. And next, showing that they have infinitely many solutions. So suppose we have this problem, y is equal to 2x minus 4 and 2x minus y minus 4 is equal to 0. So method number 1, solve for it. So we get y is equal to 2x minus 4 for the second one as well. You can add y here to make it simple, and you would get y is equal to 2x minus 4. So the next way to do it is by graphing the same line. So graph. And we have y is equal to 2x minus 4. So we just need to graph one of these lines because both of them are basically the same. So y is equal to 2x minus 4. Y-intercept would be 0, negative 4. And the x-intercept would be 2, 0. So, and then we can connect these lines. And then you could just say, since both of these have the same exact line, these two are coinciding, which means that infinitely many solutions. So now let's look at solving linear inequalities. So linear equality is similar to a linear equation, but instead of an equal symbol, we instead see an inequality symbol. So the solution of an inequality is any ordered pair that makes the inequality true, which means that there's multiple different points of intersection. Whereas, whenever there's a greater than, / less than sign, or equal to sign, the line graphed for linear equalities is solid. So suppose we have such lines, then for that one we'd have a bolded line. Whereas suppose we have such symbols, then instead we have a dashed line. So the step-by-step process for solving linear inequalities is first you solve for y. So you have suppose you have y is you have 3 plus x plus y is greater than 0. Just solving for the y, which is y is greater than negative x minus 3. Next is graphing the boundary. So you basically do the same exact thing. Substitute in to find y-intercept, x-intercept. So suppose we have this one. Our x-intercept would be, so as our y-intercept would be negative 3. And our x-intercept, on the other hand, we can just, so if you substitute this with 0 and at 3 that side, we'd have negative x is less than 3. But remember that whenever you divide by a negative sign in an inequality, the inequality symbol flips. So you would get x is greater than 3, which would basically mean x is 3. So this would be your graph. So you can first treat it as a normal equality. So you would have the following line. However, as said before, I forgot. You need to make sure that you have a dashed or solid line. But in this case, since it's just greater than, it would be dashed. So yeah, this is our line. Next, so you need to shade the area which it covers. So the best way to check if you want to shade this area or this area is to first solve for 0, 0 and see if it works. So 0 greater than 0 minus 3, 0 greater than negative 3, which works. Which basically means that 0, 0 is inside this range. Thus, you can now shade it in. So you can just shade it in like so. And this area, any point around this area would be a solution. All of this area. However, if you suppose you even took point O recurring 1, it would not work. So note, a dashed line means that any point of it is not a part of the solution. Whereas a solid line, any point on it is a part of the solution. So now let's look at solving systems of linear equalities. So similar to a system of equations, a system of linear inequalities is a group of linear equalities. The solution, however, is the shared region between both of the inequalities. So similar to the way we would solve normal inequalities, we first graph the line. So suppose we have y is less than or equal to negative 2x plus 3 and y is greater than 1 by 2x minus 2. And usually we would do something like this. So for such problems, we would first have to graph them individually. So Let's keep it on the side. Let's keep it somewhere over here. Here y is less than or equal to 2x plus 3 and y is greater than 1 by 2x. So the reason I kept it here was because we're going to have to do a lot of working for such problem. Because we're told to not only graph 1, but we're told to graph 2. So first let's graph the first one. So y is less than 2x plus 3, we can treat it as a normal function to get two values. So x-intercept for this one would be 2x is greater than or equal to negative 3. So I think it would be negative 3 by 2, 0. And if you're wondering how I found the intercepts, look at my previous video on finding intercepts. So y is less than or equal to 2x plus 3, and then substitute this for 0 to get y is less than or equal to 3, meaning that 0, 3. Similarly here, y is greater than, so basically what I'm doing here is substitute 0 in for y to get the x-intercept and 0 in for x to get the y-intercept. So 0 and then 1 by 2x is less than 2 and x is less than. So 1 by 2x 2, so it would be 4. 4, 0. And also y is greater than negative 2. So negative 2. Okay, so now that we have our x and y intercept, let's first graph the first line. So our first line has points negative 3 by 2, 0. So negative 3 by 2, 0 would negative 1, 2, 3 by 2. So it would be negative 1, 1.5. So it would be over here. And 0, 3 would be, so let's graph the y, would be somewhere over here. So now let's graph a line connecting these two dots. And similarly we have 4 zeros, so 1, 2, 3, 4, 0, and 0, negative 2. So there's another. However, this line would not be dashed. It would be it would be dashed. But first, actually, let's first draw the shaded region for line number 1. So let's see if 0, 0 works. 0 is less than or equal to 0 plus 3, which is true. So make sure to have two different types of graph or points, like dashes, so that you can distinguish between the two different shaded regions. And similarly 1, 2, 3, 4, 0, 0, negative 2. Okay, we need to make sure that this is dashed. So it might look a little messy, but you'll see that 0 is greater than negative 2, which is not true, which means that it goes this way as well. So now that we see that we have two different ranges, we can conclude that this area, this bolded area, this region is the area which would give us 2 points. So for example, if we took 1, 2, 3, 4, say 4, negative 1, 2, 3, 3, let's say 4, negative 3, this point should work for both of them. So 4. So negative 3 is less than or equal to 11, which is true. So that's all I have for this video. If this video helped you with special systems and solving linear equalities, make sure to like and subscribe. And yeah, thanks for watching and I hope I see you next time. Bye.